Thanks everyone for coming back, because now I'm going to start with my punchline from last time, the thing I wanted to actually get to, and then I'll start. And so that also fits in this title, which is Chromatic Homotopy Theory Today. It's really recent work, so let's recall there was this Kn local sphere we all know and love. I don't know, maybe that's inaccurate. And the extension to the Morava E-theory or Lubin-Tate E-theory spectrum, which was a pro-Galois extension for this group, Gn. And inside of this Galois group, which is pro-finite, there was some limited supply of finite subgroups. And I said that maybe we want to study the homotopy fixed points for these finite subgroups as a sort of step towards understanding the Kn local sphere. Maybe for other reasons as well. If P is 2 and N is 2 to the K minus 1 times some number M, maybe we want it to be odd, maybe not. But if M is odd, then maximal 2, like finite 2 subgroup inside. Yes, okay, well, I have too many caveats to your statement. So let's just say there are, in this case, no matter what, there is a finite subgroup that's cyclic of order 2 to the K. Not much more than that, okay? So Leonard, Meyer, Dan Ishii, and Minhong Zhang showed that, well, in the if we're trying to understand the homotopy fixed point, for example, homotopy fixed point spectral sequence for En HC2 to the K, what we need to do is to, so we have, yeah, so there is going to be differentials are of two kinds. There are sort of some new well, maybe new doesn't make sense. So there's differentials from lower height, okay? So then there's sort of, I'll just put this in quotation marks. So there's sheared differentials from En over 2. So we decrease, we half the height, and that sort of also halves the group that we're considering. And of course you can iterate this. So, you know, that means, for example, if you look at C4 acting on E2, this will have some differentials that come from E1, which we said we know it's P completed K theory. Maybe I need to say P is 2, with C2 homotopy fixed points. So that's a computation, that's standard, classical computation for the homotopy groups of KO, the OK theory. And then there's also going to be some new differentials, okay? The way this is done is to really use the genuine equivariant structure problem with approaching this this kind of question directly is that there's no sort of direct relationship between the subgroups of Morava, of like the Morava stabilizer group at height, at different heights. They don't really talk to each other in any direct way, but the idea is that if you look at sort of connective and C to the K equivariant model or version of En with its action, and that is a version of this truncated real Brown-Peterson spectrum where, okay, we said this kind of thing is going to be a C2 spectrum where that C2 is a complex conjugation, and then we norm that up to this group C2 to the K. Okay. So this is now a connective spectrum and has a slice spectral sequence and that talks to the homotopy fixed point spectral sequence over there. And what happens here is that there's sort of like in the slice spectral sequence. So what is the slice spectral sequence? It is a version of, well, the slice filtration is a version of a Postnikov, equivariant Postnikov filtration. So it's something that was used to a great effect in the solution of the covariant-variant problem. So there's a line of slope 1 under which we have sort of the new stuff for C let's say okay, the shorthand notation for this is BP, and maybe it's not so shorthand, C2 to the K, but I'll just write this as for C2 to the K. Then there's a line, maybe I should use colors, but of does the purple show?
Yes.
Okay, great. Slope 3, which is 2 square minus 1, and in between here, there are sort of different, the D 2 to the R, 2R minus 1 differentials correspond, sort of, let's put it this way, correspond to the DR differentials for, now the point of the comparison and somehow the key observation is that we should be taking the quotient of this group here, C2 to the K mod C2 to, and then this continues.
Not very easy to read.
That is not very easy to read. Okay, I believe that. Okay, so let's rewrite that. So here, this is the new region. In this region 1, the sort of the key information that's happening is that the new D2R minus 1 comes from dr for the quotient 2. And then there's a next region in which sort of the, I don't know what it is now. Okay. Rather than trying to write down the general formula, I just say sort of, if we had a D3 here, the old D3 here becomes D5. Here, let's say the old D3 for C2 to the K mod C4 becomes the D9, etc. Okay. So I'm not trying to do a specific computation. What I'm trying to do is give, a sketch of a spectral sequence, a little bit more precise than the one Leonard gave, but not much more precise. But the upshot here is that that this is kind of the first and only sort of systematic. I mean, it builds on other kind of systematic understanding of differentials in these equivariant settings that, due to Hill, Hopkins, and Ravenel, and transchromatic. It sort of, but it sort of relates chromatic height to the sort of the order of these cyclic groups, to the size of groups. So these spectra here, a priori, they sort of start as sort of knowing things up to height m, but then they get upgraded using the equivariance to something that knows about higher heights. And I find that to be really cool. All right. Any questions at this point? So that was kind of like as John corrected me, it's not the introduction last time, and what I just did. It was rather a survey, and it was the kind of survey that, you may imagine some kind of, I don't know, flying at high speed over a large, a landscape, and you survey the landscape at that kind of level of precision, but you get to see a lot of stuff. So I'm going to try to get a bit more focus and give a somewhat pedestrian survey of some other new ideas in chromatic homotopy theory now. Okay, I'll pause again for questions, because now I just rambled on for a while and maybe you thought of something to ask. Maybe not. All right. So, so we have this extension, the KN local sphere, to the Morava E theory, and so this is a really nice extension. And I said this word pro-Galois, and I talked about descent last time. Maybe I'll just say a little more about what this means. Okay, so we have this profinite group that acts in a sense, in this continuous sense on whatever that means, on E, and the group itself, so we said it's profinite, so that means it's an inverse limit of finite quotients. This can be actually made very concrete, and there's a small enough system of such open subgroups. So then the statement of pro-Galois ness of this being a pro-Galois extension contains the following statements that in fact for each of these open subgroups U that we have a finite extension so we can take the fixed points for the open subgroup, and now this is a finite Gn mod U Galois extension. And what that means is quite concrete. It means that the homotopy fixed points for this finite group action give you back the sphere, and it means that there's sort of a normal basis theorem. So if we tensor this extension with itself over the ring, we get a free module, free and transitive for this action as well. Okay, so but then there's a little bit more about the sort of this continuity, or I'm not sure what words I want to use, which is that in fact En itself is, well, at least in the Kn local category, is the colimit of these finite extensions. So this is the kind of the setup that sort of maybe encodes the fact that we have such nice descent properties like we talked about last time. Okay? So let's talk about some specific finite quotients here. There, I'm talking about this group Gn as if it's a very abstract thing, but it's actually a very concrete thing. And it can be represented as a subgroup of a matrix group, and as such has a determinant map. There's all kinds of descriptions, more natural than what I said, what this determinant means, and it lands in the p-adic units. So we can, this is not a finite quotient, but we can quotient it to be finite, and then we get some kind of k-truncated determinant map. And so the Galois correspondence theorem for things like this, due to John Rognus, gives us that this quotient indeed does correspond. I mean, somehow it's all embedded in there. This quotient does correspond to a Galois extension. We take the homotopy fixed points for the kernel of that determinant, and then we have a residual action. Okay. So that's a nice finite Galois extension. And I guess what I want to talk about today is the fact that, some great work due to Hermeli, Schlonk, and Janowski, in which they interpret these extensions as higher chromatic cyclotomic extensions, and in fact lift them to extensions of the Tn local sphere. Okay, so and why? So today we want to see these as cyclotomic extensions beyond the simple observation that, okay, well, there is a the cyclotomic extensions in number theory have these kinds of Galois groups. So this Kn local sphere. So for whatever reason, I decided not to give this group a different name, sort of. But anyway, so we want to. Higher, I don't know, chromatic cyclotomic extension. Okay, so this is the focus. Okay, and so that brings me to the fact that I somehow managed to talk for an hour about chromatic homotopy theory and not mention like self maps, telescopes, or any of those things. I was saving them for the special Thursday afternoon treat. All right, so, I don't think I even mentioned the nilpotence and periodicity paper at all, which is, I don't know, embarrassing to. I don't know, or an accomplishment, depending on. It was hiding somewhere. Okay, so so to talk about even what Tn is, or the Tn local sphere, we need to talk about sort of the geometric origin of the VIs that I was only talking about the algebraic sort of provenance of these elements. This is something that comes from formal groups. Okay, so I'll start. So I guess then that's Hopkins and Smith. Proved some amazing theorems about chromatic homotopy theory. In fact, maybe sort of turned the observations of whatever was happening before into an actual field of math. I don't know. So if we look at, say, P local spectra, the compact object, so the finite P local spectra, then inside of it, we get the filtration by just checking whether a finite spectrum has zero or non-zero Kn homology. So we have the K0 is cyclics, and then K1 is cyclics, and so on. What they showed is that these inclusions here are all strict. This is a full classification of the thick subcategories of finite spectra, and there's a characterization for things that are like spaces which are in one of these but not the other. So X admits so X in here, it's called a Vn self-map. I guess we've seen something about equivariant, such things, in Marx's talk. So what does that mean? It means that there's a map from some shift of X to itself, so that's a self-map, such that well, if we take the homology, the Km homology of this map, we get an isomorphism if M equals N, and we get something nilpotent if M is not equal to N. Okay, so that's what that means. And the characterization is that X admits a Vn self-map. In fact, we can even be more specific. So that this is Vn P. So it's multiplication by the element Vn, the sort of the Vn that comes from K. Kn if n equals m, and it's 0 otherwise. Okay, when does this happen? So that happens exactly. K x is K n minus 1 is cyclic. For this to be interesting, I guess x should be not Kn is cyclic, otherwise there's lots of, well, okay. There's a canonical isomorphism from 0 to 0. Yeah. So, and also, these are also essentially U. in some precise sense. And so these self-maps allow us to define sort of Tn, like the telescope Tn. Well, maybe I should mention. Okay, so the sphere itself, as known, has a V0, which is P self-map. I'm talking about P local sphere. So this is that, and then if we take the co-fiber of this, that's the Moore spectrum. It admits a V1 self-map. If you mod out by that, then you can find a V2 self-map and so on. And sort of a, well, why these things are interesting also in the direct relation to the homotopy groups of spheres, sort of having these self-maps lets you also construct certain elements in the homotopy groups of the spheres. Okay, so if we have X, which is a type N complex, then the telescope, well, if it's type N, it has a Vn self-map, so we can invert it. There's some choices. We had to choose X, we had to choose V, but the localization at Tn doesn't depend on those choices. And that's sort of also depends on this essential uniqueness. Okay. All right. Any questions so far? So as a side note here, because it's impossible to ignore, but also impossible to actually give proper attention. You might have heard of this telescope conjecture. So the conjecture, which I guess Ravenel made and then soon believed it's false, is that the KM local spectra is, well, okay, it's a subcategory of TN local spectra. That's not too hard. But this is an equality. This was shown to be true. Maybe motivation for making the conjecture as well. When n is, well, and when n is 0, it's kind of here, and when n is 1, this is due to Mahold at the prime 2, and Miller at the prime, at the odd prime. And it's false for n greater than or equal to 2 due to this amazing, incredible work by Birkeland, Hahn, Levy, and Schlank. So that's been the brand new, developments in chromatic homotopy theory that I don't know, are the exciting thing the past couple of years. I think it's about a year and a half ago this proof was announced in Oxford as part of INI follow-up events to the previous homotopy theory program from 2018. So I don't know. It's like all related to something about programs at the Newton Institute. I don't know. All right. you know, just disproving the conjecture, you know, you may or may not care about, but this was made possible, and in its creation has sort of constructed these folks have, you know, and collaborators have created so much new math in this field that I don't know. I think it's a really exciting time to be working in chromatic homotopy theory. So, all right, where are we? Are there any questions? So we have this inclusion, and there's also then a localization functor back. So so from Tn local spectra, we can localize to Kn local spectra. And then we can, again, look at this functor to Kn local En modules. And I guess last time I talked about the fact that we can get the Kn local category as the sort of homotopy fixed points of this easier category. And in particular, this is a nice sort of conservative functor. Okay, so this is great. And maybe other adjectives, positive connotation. So, you know, if you're just looking at this statement here and says like, okay, well, this inclusion is not an equality, so who knows what kind of zoo, you know, it's still like a really, you know, who knows how complicated the localization functor is and so on. And it necessarily is, well, at least it's not the identity functor. So I just want to talk about like a small, good, I don't know, small is not the right word. So I've been talking about these like big ideas and all kinds of things, but maybe I found it interesting that sort of there's a nice property of this functor that makes a lot of things work and sort of makes the Tn local category somewhat accessible. And so that's this lemma that this Kn localization functor, so not the whole one from all spectra, is what's called nil conservative, which means that it is conservative on rings. If R is an algebra in Tn local spectra, and its Kn localization is trivial, then R was trivial to begin with.
How much algebra do you need for that? A infinity, E infinity, homotopy?
I think A infinity definitely does it. But I don't think you need all that. I think this sort of homotopy.
What was the answer?
Homotopy right unit. You need a unit, but that's yeah. And I mean, the idea of the proof here is really just an application of the nilpotence results of Vesna Hopkins and Smith. You know, if we have such R, in fact, all Km localizations of R will be 0, because if you have something Tn local and you Km localize it for m different than n, it's always going to be trivial. So in other words, the support of this Tn is just Kn. And so So now you have a ring so that all of its localizations are 0, and then by nilpotence and periodicity, we get that the unit map from the sphere to R is nilpotent. But if the unit is nilpotent, then it has to be 0. Okay. So the great thing about having this kind of conservativity on rings is that oh well, okay, so let's not talk. This functor is fine, we proved it, but this is conservative, so the composite is also going to be to have this property, okay? So the corollary of this is that this composite functor is also such, okay? So these kinds of functors are then conservative on dualizable objects because you can detect if a dualizable object is 0 by looking at its endomorphism ring. So it's sort of so if you have a dualizable object in the Tn local category, you can understand it by smashing it with En and Kn localized. And it also means that you can detect whether something in pi 0 of the Tn local sphere, which is the monoidal unit in the Tn local category, if you can detect if this is invertible by checking whether the image of A in pi naught of EDN is invertible. So that image is also going to land in the invariant for our Morava stabilizer group action, and so that's, there's not that many of those invertible objects. So this is a key input or sort of observation that makes the Tn local category infinity semi-additive. So I guess I'm citing another paper by Carmeli Schlank and Janowski on the sort of ambidexterity. I'll just say paper. Maybe I should say papers. There's a few. Okay. So I haven't. What have I done? So I just I don't know. I just wanted to spend the time doing a I don't know, something straightforward because I didn't prove anything last time. So maybe now we can say there's a proof of something in there, at least a sketch of a proof. So my goal is to talk about these cyclotomic extensions. So what are cyclotomic extensions classically? They are, well, we adjoin some primitive roots of unity to some ring, and we study that extension. So, so how do we do that? Well, maybe first we look at all roots of unity, and then we check which are the primitive ones. Okay, so. So mu, let's just look at this P to the R because that's the thing we had. So P to the R roots affinity in some ring R, wherever that is. Well, okay, it's a functor that's sort of co-represented. So just literally, it's the maps in sort of groups of some sort. I don't know, whatever. We try to map CP to the R into the units of R. And if we want, we can rewrite this as maps in algebras from, say, the group ring of P to the R to R. Okay, there's a junction that makes that happen. And the idea is to do a higher version of this. Let's see this yellow work. So now R maybe will be some spectrum, or sorry, well, an algebra, commutative algebra and spectra, maybe localized in some world, or maybe something more general than that. And then, okay, well, instead of groups, we're gonna have, or like abelian groups, we're gonna have something like connective spectra. Then this units, well, it's a space or infinite loop space, so it's again a spectrum. So this kind of thing is well known. Maybe you've seen it under the name of GL1 of R. And here, wait, I should have said R algebras here, and that would still work. Okay, so okay, except not quite. Well, no, that's fine. Okay, so we can define this. There's nothing. Okay, this is not the higher. Okay, for spectra. Okay. So, if we wanted to talk about so where the higher comes from, let's use some more color. So we're gonna stick an N here, and what we're gonna do is just take loops. Shouldn't have done this. Okay. We're just gonna take n-fold loops. That's all. Okay. So now that puts a loop in there, and puts a. Leave enough space. The looping in there, okay? Is it clear what I should have? I'm trying to optimize for time, instead I'm doing the opposite. I mean, I guess in the idea is all of this, okay? I mean, it's not, right, so we didn't do something too complicated, but so the way you would check whether these sorts of things are primitive, well, you have a P to the R primitive root affinity if it's not P to the R minus 1 sort of proper root affinity. So what that would mean is that if you have like something in here, well, that's a map. You see P to the R to loops n of R cross. We have this surjection to P to the R minus 1. And then, well, for any map of algebras here, if we're going to have an extension, well, so if there's an extension, there's only an extension only for the zero ring. Okay, so we don't actually have this after base change. So so then we take the connected components of this space, and that correspond to the primitive ones, and that gives you a mu p to the r and prim of r. Okay, so just by construction, here we see that the roots, so this functor mu p to the r n is co-represented by, in our algebras, by, say, r v to the n v p r. So this group ring. And if we have something like the Tn local or Kn local category, then the primitive roots of unity, this higher mu p to the rn primitive, is also co-represented by some ring, and that's our cyclotomic extension, because that's how, well, that's how it works in algebra for just a regular regular things. So how do I want to say this? Well, okay, here. Theorem is that, let's put it this way. So for let's say R a Tn, yeah, let's use algebra in Tn local spectra. The representing object, therefore, mu splits as sort of mu, the thing representing one power of p lower, roots of unity, and the primitive roots of unity. These are higher roots of unity, and this ring represents or co-represents mu n p to the r. Okay. Oh, yes. Thank you. So I'll just make some comments about this, but maybe first I'll pause for questions. The raise a board. Maybe I shouldn't.
Say again what primitive means.
Okay, so primitive means that every time we always have this left-hand surjection of groups, right? Now, every time we have an algebra map from R to S, we have an induced vertical map, and then if that algebra S is not 0, then we can't make a diagram commute like that. Yeah. Anything else? So in fact, in this kind of setting, like the Tn local or Kn local spectra, so the general categorical property there is infinity semi-additive of height n. This functor of say primitive or all roots of unity is a functor to sets and not just spaces. So mu p to the r n and mu p to the r n prim. Its functors sort of go from, say, commutative algebras and Tn local spectra to sets and not just spaces. And the reason for this, well, it's kind of comes from the study of ambidexterity and height in these contexts. So again, sort of these ambidexterity papers give that so if we have any n-connected pi finite space A, then I don't know anymore if my indices are right. N connected, whatever. Okay, B n plus 1 is n connected. Okay, that's fine. Then this thing by which we mean sort of the Kn local suspension spectrum of A plus, then this thing sort of it just is just a Tn local sphere. And so that's the sort of the infinity semi-additive of height 1 condition. That something like this is true. It's sort of, you know, where is this? Height n. Where is this coming from? You know, computationally. This kind of fact is traceable back to the Ravenel-Wilson computation of the Kn homology of these kinds of spaces. So there's that. Why this thing then implies that the functor just mu p to the r is n truncated, so then when we loop it n times, we get something discrete. Okay. Something else to say is that, okay, where is this splitting coming from? Well, okay, a splitting like this comes from an idempotent, and you know, I've talked about our algebras in here, but you know, we could just look at the sphere, Tn local, and smash with those things. So they all come from there. So the idempotent there, splitting the primitive roots of unity comes, well, is there's a lot of writing in this as well. So this idempotent is 1 minus epsilon, where epsilon is this funny expression, where there's some kind of division by the cardinality of B and Cp of this sort of similar kind of thing in integral. We get to sum in this kind of setting of infinity semi-additive categories. We get to sum over spaces, or pi finite spaces. So I guess Mike talked about how this sort of perspective on monoids, Siegel's perspective, where we get to sort of add over, like have sums or things like that, indexed over, say, sets or G sets or things. And so in this infinity semi-additive categories, we get to add with indexed over a space, these, well, by finite space, which means it has finitely many finite homotopy groups. And maybe I didn't say what I is, but maybe I won't do that. And so then to end, I will still keep this in the shape of a comment here. The Tn, so if we look at this Tn local sphere, the corresponding extension, this is a faithful Galois extension for the group Z mod P to the k units. And where's the action coming from? We can see up there that the sort of, automorphisms of Cp to the R act on these spaces and are compatible with these splittings. So this is a nice extension. This is a dualizable module, and then after Kn localizing, it becomes this extension that we talked about. Okay. All right, and so, okay, so I don't have any more talks, so I will end here. Thank you.
Was the exponent of the P in the Z mod P to something across?
Oh, great. R and K became the same thing.
Okay, it should be R.
R. Yes. That's R, and then I would need to put an R here to make them match. Yeah.
More questions? Yeah. If you look at the extension you have in the Kn local category, was there like a reason to think that I should view that as cyclotomic in some sense? Outside of the Tn local category?
Yeah, the same. So in the K local category, would have the same kind of representability result. Yeah. So these are also these sort of higher cyclotomic extensions, Kn locally.
They are also abelian extensions. So there's the Kronecker-Weber theorem that abelian extensions of Q are precisely cyclotomic extensions.
Exactly. Thank you. So these are. That's right. So these are abelian. Okay, there's that, and that's reminded me of, well, I don't know, of a question you might ask. Can you lift other finite extensions, the Kn local finite extensions, to the Tn local setting? And I am told that there's work in progress on this topic that positively answers this question. So done by Clausen, Levy, and who is it? Robert or Berglund?
Okay. More questions? There was a question, yeah.
So, how do you do this identification after the
Right.
localization?
Thanks. So the characterization, after you know it's a Galois extension for this, then you simply need to figure out, sort of, you can use the Galois correspondence, so you just need to figure out sort of which character does it correspond to. Okay. And so I call that a determinant map. The way these things are built with the sort of the relationship to these BNs also gives a determinant interpretation. So sort of relating to the Hopkins and Lurie approach to ambidexterity, where the sort of exterior powers of the formal group law come into play. And so that's gives you connection with the sort of top exterior power of something is the determinant. So.
More questions? If not, let's thank Vesna again.